Welcome everyone to this webinar on climate change data, which will be presented by Lu Li and Ole from NORCE. I'll just shortly introduce myself. My name is Line Hansen. I'm the program leader of Program 3 in RenewHydro. Just a few slides just about RenewHydro for anyone who might not be very familiar with this new research center. So I just wanted to say that this is just the RenewHydro organization. And as you can see down on the research programs, why Program 3 is taking the initiative to this webinar with Lu Li and Ole Wulff from NORCE is that I'm the program leader of research program 3. And the topic here is hydropower in a changing climate. And then it's very important for us to have this future climate data scenarios and have the expertise from NORCE, which allows us to connect this with hydropower in the future climate. And also in framework program, which is this program, there's a project called Trends in Runoff on the Climate Change and Effects on Hydropower Production, where a lot of this expertise sits, which is being led by Øyvind Påske. So especially this project and research program 3 are very connected to this climate change data. So with this, I would just like to introduce Lu Li and Ole Wulff, and thank you for presenting their research and how this can be used into RenewHydro.
Thank you. Yes, I'll be starting. Lu and I will be sharing this presentation, and I just want to say I'll start with a bit of a more general introduction, and Lu will go into more details on the actual hard science that's being done. So I'm Ole Wulff. I'm in NORCE Climate, so is Lu. We're both climate scientists, Lu a bit more of a hydrologist. And we'll be presenting you something on simulating future climate today, predictions to projections. Let me start with a short outline of what I'm going to talk about. First, I would like to motivate a bit, why do we simulate future climate at all? Then say something about how we do it, the different approaches to modeling, global and regional. Then talk a bit about climate data or climate information that is available to us, first of the past, but also of the future. And here I'll be talking about predictions and projections, as well as be addressing uncertainties in these simulations, and finish off with a small example of applied work until Lu will then take over. Okay, so let's just start with this small example here, and just for the sake of this example, assume you see here a time series of something that is a very good indicator of how much hydropower you can produce in a certain region, right? This red line here. So you see there seems to be a slight upward trend. So maybe it's worth going into this area and investing into it, maybe building a power plant there. You might do that. The next 10 years play out, and it seems like, well, it didn't quite turn out as you expected, right? If you look at this, then you would rather say, okay, it's rather flat. That might still be okay for you. Now the next 10 years turn out, and you're suddenly in a very different regime. These values have dropped a lot. Suddenly, you might go from a very profitable project to one that is running at a deficit. This is an actual example of terrestrial water storage in South Central Brazil, something that didn't just affect the hydropower market in Brazil a lot during especially 2021, but also the water supply there. Where basically the region experienced severe drought for an unprecedented drought for a certain period of time, leading to large ramifications. And the point that I want to bring across here is basically that just the past alone, looking at the past alone, is not really a useful indicator of the future, right? And I mean, this might sound a bit naive in the way that I bring this argument here, but we often actually do this. If you think about, for instance, how we treat the occurrence of seasons, right? We often expect to spring to start around the same time during the year, or the winter to begin at the same time of the year. When in actual fact, we know that these things are also changing. So for instance, you see flowers blooming earlier, but also you see spring floods occurring a lot earlier during the year nowadays. And the main, although not the only reason for this, is of course an accelerating anthropogenic climate change. And what it does is that basically it questions a bit these experience that we have based on our experience of the past. But the good thing is there is something we can do with climate models. We can simulate some of these changes, and we can even predict some of these changes. So that's why I think climate modeling will be very useful to the center as well. So how do we simulate the climate system? Well, basically, we try to model how water, air, and also energy is exchanged inside the atmosphere, sea ice, oceans, ice sheets, land surface, and in between all of these components. And we do this based on the physical laws of nature, right? So we don't just take a time series, as I just did now, and sort of make some statistical assumption that it will continue or stay as it is, but instead we use the physical laws of nature to model these flows. And how we do it in reality is that we take the globe, and we can't do this at sort of an infinitely fine resolution. We sort of have to cut the globe into a mesh of grid boxes of finite size. And then we can exchange water and air and energy between these grid boxes. But that also means that the model doesn't really see what's going on below the scale of these grid boxes, right? So a mountain that you might be seeing out of your window might not be visible to a model because the size of these grid boxes is ultimately limited by how much computing power we have. You might have heard that these climate models run on some of the largest supercomputers in the world. So these are very expensive simulations. They have to simulate billions of parameters at the same time, which of course imposes a very strong restriction on these simulations. And in general, they have to be run globally in a global model or a GCM. And this is why these scales are typically restricted to about 30 to 100 kilometers. 30 would already be quite high. And these global models do a reasonably good job at simulating the climate general circulation, but of course they will lack some detail, right? So for instance, in the orography, as I said, or the coastline, and related to that, they will also be lacking a lot of detail in certain small scale processes and especially extremes. So here is an example of what the grid of such a global model would look like, and you see the Scandinavian mountains here are basically completely smeared out. But what we can do, even though I said we can't just cut off the model at some arbitrary place, we can take a global simulation and then run a regional simulation, so within restricted boundaries, inside this global simulation, basically, a so-called regional model or regional climate model or an RCM. And there we can basically put many or the same number of grid boxes that we first had to distribute over the entire globe just into this one region, so we get a lot higher resolution, right? And now suddenly you see features appearing like the mountain ranges here. And basically the information at the boundary, which of course also matters, comes from such a global simulation as we see on the other side. So we often say that these regional models, they downscale global climate simulations, or it's a dynamical downscaling is what we often refer to. And these have much higher spatial scales. So these can be from, let's say, around 3 to 25 kilometers. And I think Lou will show a lot more concrete examples of these. And since these offer a lot more detail, these are the ones that are a lot more useful for regional applications and as input to, for instance, impact models, as we will probably use them for a lot in the center. Okay, now to get to what sort of information is available. Let's first talk about past climate. Maybe in the beginning I said, well, the past is not necessarily a good indicator of the future. And while that's true, that doesn't mean that past climate data is useless. In fact, it's probably the most useful data we can think of. Without any past climate data, we will never have a future simulation, right? And the sort of information that is available here is for instance, direct observations from, for example, weather stations or weather balloons. Then since about the 1980s, we also have a good coverage of remote sensing data. So that means satellites and radars, for instance. But the problem with these is, although they're very useful and extremely good data sets, they are often a bit limited in time or in space. So they don't offer the same regularity in time and space as, for instance, a model does. So some very clever scientists, climate scientists, have come up with a method basically to combine all of these observations and put them into a data set that gives us a best estimate of the true climate state in this model world. So in this very spatially and temporally regular world of the model. And the way to do it is basically to combine the observations in a clever way, not just to interpolate them, but actually use a climate model to produce a physically consistent state of the climate within this climate model world. And there are certainly data sets that are of extreme usefulness. You'll probably see them being used a lot as information on past climate. They exist on a global scale. So for instance, ERA5, which is at a resolution of about 31 kilometers. Soon, I think by the end of this year, they will start releasing ERA6, which is almost or even more than twice the resolution of it. And maybe just as a side note, you might have heard of the revolution in weather forecasting using machine learning models. These machine learning models are basically trained on these reanalysis data sets, namely ERA5. So even though they claim to replace the physical models, they are actually based on the output of exactly these models. There are also some regional reanalysis. For Norway, most important is probably NORCE at a resolution of about 3 kilometers, but also things like SERA, which is a European reanalysis at about 5.5 kilometers resolution. If we want to look into the, oh, sorry, I forgot this. This is just to illustrate that these observations go into a model to produce a reanalysis. If we now move into the future, then it basically depends a bit on what kind of timescale we want to look at. So all of you are probably well familiar with weather forecasts, right? Where for the next day, we say something about the actual concrete values of precipitation or temperature, for instance. But we have predictions on many timescales going even further out. So something we call subseasonal to seasonal predictions, where, for instance, for weeks out into the future, we try to say something about the likelihood of occurrence of a storm or a heat wave, for instance. There's seasonal forecasts that try to inform about the tendencies for a certain year to be warm or cold or wet or dry. And there's even decadal predictions that try to give some information on the long-term tendencies. Say in the next 8 to 10 years, will we be more likely to have more drier winters, for instance? And the important thing here is that these are predictions. What does that mean? In technical terms, it means it's an initial value problem. And that just means that how the climate system looks today is what matters most for these. So we need a very good estimate of the state of the climate system today to be able to make a prediction. This includes, for instance, right, we need to know which season are we in. We can't, very naively speaking now, but we can't expect to have a good forecast for tomorrow if our model thinks it is in November when we started, right? We need good information on these initial conditions. We need to know which season we're in, whether the ocean outside is warm or cold, whether the soils are dry or wet, and we need to know this with a lot of detail to be able to make good predictions. Examples of these predictions include, for instance, the year 21-day forecast that some of you might have seen. It's been released last year. as an extension to the standard year weather forecast. There's seasonal predictions, for instance, from the Copernicus Climate Change Service, or C3S in short. There's also decadal predictions. You might have heard of the Decadal Climate Prediction Project, or DCPP. And the important thing about these predictions is that they make use of this information of what is now, and they make a prediction out of that using a climate model. If we want to look past, say, 5 to 10 years, maybe up to the next decade, next centuries, then we're faced with a different problem. Because here we're talking about a forced boundary condition problem. What that means is that things that the climate model does not simulate within itself matter most. And one important, if not the only, though not the only aspect of this, is human decisions, right? So these climate models, though they model a lot of different components, they don't have like we don't simulate little humans inside these boxes that look outside and make decisions and organize and try to mitigate climate change or anything. But instead we have to make certain assumptions and think of certain scenarios, because the decisions that we take result in changes in emissions of greenhouse gases or of aerosols, for instance. They result in changes in land use, and these things matter for the climate. So basically what we do here is we think of a bunch of different scenarios that could be likely, and we model how the climate system would react to these changes that we make. So these are called predictions, and they're in some way quite fundamentally different, even though the approach to make them is to some degree similar. Examples here include CMIP 5 or 6, or hopefully soon also 7. These are global climate simulations. And basically CMIP is a certain protocol for producing these a bunch of these predictions, just a standardized protocol to be able to prepare all of the to compare all of these simulations. Then on a regional scale, we have something that is called Cordex. So there we basically take these global simulations and we zoom into certain regions, again, to have more detail, higher resolution, better information on extremes and local conditions, for instance. Okay, sorry. So just to wrap up, if you're interested in decades and longer, go to projections. In fact, you won't even find any predictions or anything that claims to be a prediction for the next 100 years. More importantly, if you're interested in something below a decade or shorter than a decade, don't turn to projections. Rather try to use predictions. And the reason is not that projections will be wrong per se, but they probably have more uncertainty than is necessary. We can actually be a bit more certain about the estimates we have on these shorter timescales. And that brings me to the uncertainties that I want to talk about, because of course these models, with these models, we don't claim to know it all, right? We don't just put in the best estimate of today, and then we produce one line, one trajectory of where the climate goes, and we say this is it. This is what it's going to look like. Of course, there are uncertainties, and there are some that we know about and that we explicitly try to model as well. So one is this, what I call here now state uncertainty. So I said for the predictions, it's important that we have very exact knowledge of the current conditions of the climate system, but we cannot have perfect knowledge of them, right? And actually, even the slightest deviations from the truth will lead to uncertainties and errors. Even if we knew it perfectly well, we couldn't even represent it in a computer. And this is something you might have heard of as being referred to as the butterfly effect. If we go out longer, then of course these scenarios introduce some uncertainty, right? We have to make certain assumptions. We don't know what kind of pathway our society will go on to. So this, especially longer out, of course, produces a lot of uncertainty. And then we also admit that even though we've put a lot of time in developing these models, there is scientific uncertainty or model error. These models are just plain not perfect. Part of the reason is that we have to cut them off at a certain scale, as I mentioned, with these grid boxes. But there might also be other errors in these. And just as an illustration, I show you this figure on this side. So up until where it starts being colorful, this is the past basically. And then we try to model the future, and you see that these three different components of uncertainty are represented by different colors. So the orange would be this now state or internal variability uncertainty. The blue would be the errors or the scientific uncertainty, the model error, and green would be would represent the uncertainty in the scenarios. And you see that on these shorter timescales where we talk about predictions, it's really the internal variability and the model error that matter most. And only if you go out to multiple decades, then it will be important sort of what assumptions we make about how humanity will basically evolve. How do we address these uncertainties? We use something that we call ensembles. So we use different now states, different scenarios, and different models. And we make multiple of these runs. We don't just make one best estimate. We make multiple of these runs and produce multiple outcomes of future climate. And all of these runs are basically, as far as we know, equally likely, but all very, very different. And by this, we can basically quantify the uncertainty of these simulations. Okay, I also want to give you a quick example of how we can use climate prediction in more very hydropower related application. So one thing I've did together with colleagues from NORCE Climate Environment and Småkraft is that we took this year 21-day forecast that you can download through their API. And we basically use it as input to a hydrological model, in this case, an HBB model, and we produce streamflow predictions out to 3 weeks based on these forecasts and the hydrological model. And we made this into a small planning tool for Småkraft, or generally small-scale hydropower, which produces probabilistic predictions of river discharge at individual plants. So importantly, this also covers this aspect of uncertainty by giving an ensemble or a probabilistic prediction, right? Where we basically don't just simulate one truth, but a range of possible outcomes. Okay, let me wrap up my first part. I hope I could convince you that accelerating climate change means that the past becomes less and less useful as an indicator of the future. I discussed changes in the seasonal cycle, right? Basically spring starting earlier, or also the occurrence of extremes, right? There's many examples of events that we previously assumed to be maybe 200-year events now occurring a lot more frequently. So the past becomes less and less useful as an indicator of the future. Climate models, on the other hand, can give us a somewhat better idea of what to expect. They're also not perfect. I also discussed that, but they also they can give us some ideas on these changes. In general, regional simulations are probably better suited for impact studies, as we will be interested in this project. If you're interested in information out to the next 10 years or so, rather use predictions. If you want to go beyond that, you probably should turn to projections. And as a last point that I also illustrated last year was that uncertainties definitely need to be taken into account. And ideally, don't just use one simulation, but try to use multiple to get a bit of an idea of these uncertainties. Of course, everything is to some degree a bit restricted by the computational power we have available, right? If you make a very high resolution simulation, you probably won't have the resources to make many different runs to quantify the uncertainty very well. But yeah, I'll end it at that and hand over to Lou.
Thanks a lot, Ola. Hello, everyone, and thank you for staying with us for the second part of this presentation. And I'm Lu Li, researcher in NORCE Climate. Like Ola said, I'm mainly hydrologist, while in the past 10 years, I have worked a lot on the interface between regional climate model and hydrology. So I will now take over and introduce different types of regional climate models, focusing on how their resolution and structure affect the simulation of local extremes. Okay, here I will walk you through 4 main topics. First, I will explain the differences between traditional regional climate model called RCM and the newer convection permitting regional climate model, so-called CPRCM. Then I will show how the CPRCM add value at both regional and local scales. And then I will present some examples, both future projection and uncertainty, to show you what kind of insight these models can offer. And then finally, I will close with some key takeaways. Let's start with this figure, and which shows the nested modeling approach. So we can start from a global model, which has very cross resolution, as Wulff have mentioned, typically around 100 kilometer resolution. And to bring this information closer to the ground, we first use an intermediate resolution RCM with a grid spacing around 10 to 25 kilometers. Then to capture local processes, we nested one more model inside. This is the convection permitting regional climate model with a resolution as fine as 2 to 4 kilometers. So what is the key differences between a traditional RCM and a CPRCM? So the traditional RCM are not able to resolve convective storms like thunderstorms because their resolution is just too cross. And instead they use the simplified equations, or so-called the parameterization, to represent these processes. But the CPRCMs are different. They are fine enough resolution so to simulate those convective storms directly in a much more physical and realistic way. So this can give us a much more confidence when we're looking at extreme weather events. So previous studies have shown that convection permitting model offer a much promising improvement in representing the extreme precipitation. This is especially relevant for flood and hydropower risk assessment. And I listed some literatures here. But looking only at the national or continental average can miss key local patterns, especially in complex terrain like Norway. So here the left figure shows the winter daily precipitation biases between CPRCM and the EOBIS, which is the European graded observation data. So we know that Norway has very different climate regions between coastal and inland areas. So we really need to scale these evaluation to regional and even local scales, and to look at how these models perform across different hydroclimate zones. And that's what we've done in a recent study. I have a PhD student who have worked with me, and now this work has accepted in the HES journal. I will now show some of the results in my following slides. Now let's take a look at this density plot first. This is showing the model bias for annual maximum 1 day precipitation on the left-hand side, and then maximum 1 hour precipitation across Norway. And the different colors represent by CPRCM is orange, and then blue color lines is from RCM. So what we can see from the figure, basically this y-axis show how often a given bias occurs across all the model grids. And if it has a narrow peak, means this consistent bias across the region. And if it has a wider spread, that means there's more variability, and meaning the model behavior differently depending on what the location or the different conditions. And it has also the left or right skewed curve, and that means the model tends to underestimate the extreme or overestimate extreme respectively. So we can see that the CPRCM performs better on average for the daily maximum 1 day precipitation, with the biases clustering more closely narrow around 0. When we take a look at on the right-hand side for the hourly extreme, the CPRCM tends to slightly overestimate the extremes, while the traditional RCM mostly underestimate them. And that suggests that the CPRCM are more capable of capturing and the short and the intensive rainfall event. that which is very important for assessing local flood risks. But there's a but. So if we look at the spread in the hourly biases from the CPRCM, we can see that it's slightly wider than that from the RCMs. And this means that it has also a larger uncertainty in hourly extreme from the CPRCMs than the RCMs across Norway. Now let's zoom in to look at the seasonal and regional differences. And I'm showing this figure about the biases in seasonal maximum 1 hour precipitation across 8 regions in Norway. And we can clearly see that the RCM consistently underestimates the hourly extremes across all the regions and season. So the same, the blue color is from RCM and orange represented by the CPRCMs. And we have the 8 districts, the regions over the columns, and then the seasons on the different the lines. And then on the right-hand side, this is the actually different color represent the different sub-regions in the whole Norway. So we can see the CPRCM performs notably better, especially in spring, winter, spring, and autumn. But in summer, however, they tend to slightly overestimate extremes in some of the regions. For example, like in the eastern and western Norway, and then also middle inland and the middle coastal regions. And it highlights the remaining challenge in simulating the summertime convection. So we see that the CPRCM represents a clear improvement, but there's still room for a better refinement, and particularly for convective events in a warmer season condition. So now let's take a look at the time evolution of annual maximum hourly precipitation at a station level, which is more local. This is taken from 10 rain gauge stations from 1999 to 2018. So we can see that compared with RCMs, the CPRCMs clearly track observed year-to-year changes more closely. And in some cases, they still underestimate the magnitude or get the time slightly off. But overall, they show a much better match with observations. That said, CPRCM is not perfect, but in many locations, so we can see that they're still struggling to capture the exact time and also the intensity of one single most extreme event. So there's still room for improvement, particularly when it comes to this local maximum. But on average, the convection permitting regional climate model produce the values that actually, especially if you look at the down this part, summarize all the statistical from the 10 gauges, you can see that this CPRCM actually falls within the observed ranges, while these RCMs remain consistently too slow on the bottom of the box plot. Now let's take a look at the spatial distribution of extreme precipitation evaluation. And we use the Bergen municipality as example. So here's the map shows the maximum 1 hour precipitation, comparing observations on the left-hand side with the results from both CPRCM and RCM on the middle and the right-hand side. So we can clearly see that high resolution CPRCM does a much better job at capturing spatial variability of extremes. So the values from 2 to 18 millimeter per hour, represented by dark blue to the light green and yellow. So, but if we look at the color, we can see that RCM tends dominated by the dark blue. That this means that it tends to smooth out the peaks and underestimate this most intense event. And this level of detail is especially valuable for the local hydropower operators and urban planners, also the emergency services. So it's important to actually to have the opportunity to get the higher resolution for your local extremes. But it's also important to remember that this good performance in Bergen doesn't really guarantee the similar results any other places. So we still need the local scale evaluation in the other regions if we would like to take the high resolution model into our work. So how does this look when we turn to future projections? Here, I'm still taking Bergen extreme precipitation as example. We used two different global climate models. One is the so-called drier model, and another is the wetter model. And the dry model is associated with a cooler ocean and the less atmospheric moisture, leading to weaker storms. The wetter model, on the other hand, is with a warmer ocean, and then there's more moisture that resulting in a heavier rainfall. So if we look at the results, on the left-hand side, that's control period. And then in the middle is the subfigure shows by the end of by the middle of the century, how much the extreme precipitation increased. And also on the right-hand side subfigure, that's by the end of the century, how much the extreme precipitation will be increased. And the change varies from -45% to the +45%, represented by the red color and blue color respectively. So we can find that extreme precipitation in Bergen will be increased from both GCM projections. And in the wetter model projection to the very right-hand side, and this increase is about 50% by the end of the century across all the Bergen. And I didn't mention that the dots in this map indicates where this increase is statistically significant. But we can go even further. So question is that, can the convection permitting regional climate model help us understand or see the differences within the city? Here we look at these projected changes in summer maximum 1 hour precipitation across 8 districts in Bergen. So these values are given for each of the 8 districts over Bergen municipality. So if we look at the changes and the values, the answer is yes. There are clear spatial variations showing that local scale information really matters. But there's always a but. We can also see there's a spread of future projections within each district is also quite large. For example, most of them varies from 10 to 50%, like in Osana and Anna, and to some extreme cases like Inderbygda even goes to from 20 to 70%. So this reminds us that uncertainty in climate projection, especially for extremes, is still significant. And in fact, in this case, the model uncertainty is even larger than the differences between districts. And this highlights the need for careful interpretation when using this information for local adaptation. So very quickly, let's take a look at how this translates into flooding. So here I'm gonna show you some of the hydrological modeling. We used 2 hydrological models in these future flood projections, taking a study basin at Roiknes Basin, which is near to Nestten. Here, the upper figure shows the 2005 autumn flood in Nestten. And the black polygon is showing this Roiknes Basin. And taking this simulation, in the simulation, we used 2 hydrological models. One is the Wulff Hydro. It's a physically based distributed hydrological model, and another is a lumped conceptual HPV model, so that we use two models to explore the uncertainty from a different hydrological approach. And in the projections, we also take both the drier and the wetter GCMs in the simulation. So our simulation suggests that flood peaks in this catchment could increase by around 10% by the middle of the century and up to 20% by the end of the century, comparing with the control period from 1986 to 2005. But there's also a range, uncertainty range from 1 to 20% by the middle of the century and 10 to 30% by the end of the century, depending on model input and scenarios. And these numbers show both the urgent of climate adaptation for local Bergen municipality and also the importance of aware and acknowledge the uncertainty in our decision making. Before closing, I want to show you with this final piece to connect everything we've discussed together with Ulla. And this figure shows how different type of climate information across different time scales, and that can support decisions in hydropower and water-related sectors. So on the top, we see this timeline from historical time to shorter-term weather and all the way to the multi-decadal climate projections. And along with the different ranges and different type of decisions that can come into play, like for example, for real-time operation and early warning based on the hour or days or weeks weather forecast, and also to the seasonal reservoir planning, to the strategic long-term energy or infrastructure design towards the multi-decadal projections. Here we highlight the importance of the middle step. We take the raw climate data and tailoring it with the users. That means we scaling it to the local context and testing models and then translate it into something useful. And this tailored process is what transforms raw climate output into decision support information like flood risks, drought or hydropower stress, and helping making climate data more actionable. So to wrap up, here are some key takeaways. As we've seen today, convection permitting regional climate model gives us a much more detailed information, and they help us to better simulate extreme events, especially in the regions with the complex terrain. But their uncertainty is still large, and these models are not perfect. And this result should always be interpreted with care, and especially when used for local scale decisions. That said, there's no one size fits all solution when it comes to climate data. And the kind of information you need, how far into the future, how detailed, or what kind of model, is really entirely depends on the decision that you are making and the work that you are focusing on. And that's where we can help. And the NORCE, we are happy to support you in identifying the right kind of climate data or the tools tailored for your needs. And whether you are working on hydropower operation, environmental flow, or infrastructure design. So just feel free to contact us. Thank you all very much for listening. And Ulla and I are willing to take any questions.
Excellent. Well, I would like to thank you again for this great presentation, and also to all the people that joined today. Thank you very much, and for asking questions. So thank you, everyone. Really good webinar.
Thank you, Nina, and thank you, everyone.
Thanks, everyone. Bye.
Bye-bye.